Okay, let's start. Hello everyone, and welcome to this tutorial. We will talk about meshing. So my name is Charles. I am a lead engineer at Kitware. I have a PhD in topological data analysis and some expertise about meshing, HPC, and discrete geometry. And I am with Mathieu.
Yes, so I'm Mathieu Westphal. I'm a ParaView expert engineer at Kitware, and I will be assisting today Charles with the chat. About that, you may want to make sure you have access to the chat. It should be top right on the screen. You may need to log in or just put a name in it. So do not hesitate to go into it and to say hello to all to other viewers there.
And please, if you have any question, feel free to ask them.
Of course.
We would like to keep this webinar as interactive as possible. It's not so easy, so please do your part. So today we will talk about meshing, but first a quick presentation of Kitware, because this webinar is provided for free to you by Kitware, and we are an expert corporation. We have expertise in different scientific fields, as you can see here, in scientific visualization, image processing, computer vision, and data analytics. Today we will focus on the scientific visualization parts, on which we can do HPC and provide you visual results of your acquisition or simulation on various platforms, ranging from a small mobile to a larger computer. Everything can also be viewed on the web, and we have other fields where we can help you with medical data, point cloud, and we can explore things in virtual reality too. So please ask us if you have any questions in those fields, and we would be glad to help. The way we work is by maintaining open source platforms which are provided for free to you to use and to reuse, usually BSD3 license, and they contain state-of-the-art algorithms, so they are interesting for you to use. You can take them and change them as you wish to improve things inside, and even build custom software around our solution. We will talk a bit about VTK and ParaView today, for examples, but we can also help you doing so with consulting if you have questions, with support if you need more technical and advanced topic for us to help you, and also by developing custom solution for you. If you want also help in understanding what we do and how our software solution works, we provide trainings about them. Today we will talk about meshing. There will be two parts in this webinar. The first one, it will be a short one. I will just show you how you can get ParaView and how we can enable or add plugins into ParaView, because we will then use those solutions for the mesh processing part, in which we will see how to inspect some meshes to see if they respect some precondition. Then we will see how we can improve our meshes with remeshing, local or global remeshing, and if we have time at the end, I will show you some more advanced operation that we can do with those meshes. So in this webinar, we will focus on surface meshes, which describe volumes, and that will need to be triangulated. This is because the huge amount of meshes that you can have in the real world are too various, and so we'll just focus here in this short webinar into simple case when we have triangulated surface. What are the notions that we will need through this tutorial? So a surface mesh is a 2D embedded surface in a 3D scene that usually describe a volume, and here we will ask it to be triangulated, so only composed of triangles. If your surface indeed describes a volume with a clearly defined inside and outside region, if it's closed, we will say it's a watertight surface. And if the neighborhood is always well defined around each point and each cells of your mesh, we will say it's a manifold. So you won't have like a butterfly point with two different triangles connected on it. I will show you some degenerate cases later. I think things will be more clear at this time. So first of all, how to get ParaView and the various plugins that we will use for this tutorial. For ParaView, just go into paraview.org. There is a download website, download section here, and in this website you can download all the different versions of ParaView. Of course, I would recommend you to be on the 5.13.1, which is the latest stable, and it's available for Windows, Linux, or the macOS platforms. Once you have downloaded this ParaView, you just have to extract the corresponding folder and you can use it on your computer. If you need TTK, as we will see today, it's included in the ParaView release. So I will show you how you can enable TTK into your ParaView. So here I have a ParaView folder that I have already extracted. So I just go into the bin subfolders and launch ParaView with a shell here, but you could also click on the ParaView launcher on most operating system, it would work too. And here I want to enable TTK, so I will go into the Tools, Manage Plugin windows, and here I have all the plugins which are distributed with the release of ParaView. And at the end of this list, there is a Topology Toolkit here plugin. I can enable this plugin by clicking on Load Selected, and if I don't want to have to do that again the next time I open ParaView, I can unfold the Topology Toolkit here and autoload, check the autoload section. So the next time ParaView starts, it will be enabled directly. And the last plugin that we will use through this tutorial is Westphal. Here again, we have directly a plugin that we can easily load into the ParaView release. This time it's only for Linux because we don't provide yet things for Windows or macOS. I hope it will be done in the future. For that, you would need to download this plugin from the Westphal webpage. So on the Westphal source in GitLab, you will have here a release tab. And if you click on this release tab, you have the sources of Westphal for various versions of ParaView. As I said, it's Linux only for now, but you can here download a SO file.
So just one question. This binary plugin, that's a new thing, right?
Yes, it's something that we did last week basically. So it's a new things for this tutorial that comes with the release of the 0.2 version of Westphal.
So it used to be needed to compile yourself, but
Yes.
now you can just use the binary on Linux, no compilation needed, just load it and use it.
Exactly, and I will show you how to load it. So here is my ParaView once again. We also need to go into Tools, Manage Plugin, but this time Westphal is not here directly. We need to click on the Load New, and here you just have to select the SO files that you downloaded for your version of ParaView. Okay, and the Westphal plugin will appear here. I could autoload if I wanted to. Just as a reminder, Westphal is based on the Seagull library, which is developed by Geometry Factory. That's how it provides cool geometric, discrete geometry algorithms. This library is GPL, so if you don't have any, it's dual licensing in fact, and if you do not have the commercial license of Seagull, then once you load this plugin, your ParaView becomes GPL too, so you would need to be compliant with GPL. So here is the demo time. So I will come back on my ParaView once more, and to start we will load a dataset which is obviously degenerated.
Sure. Maybe switch to...
Yeah, I will reduce the size of our heads.
You should... no, it's fine. Sorry, my bad.
And let's load a dataset which would be suitable to see non-manifold things. As you can see here, the name is quite meaningful. So I have a non-manifold dataset here, obviously. Why it's non-manifold? It's non-manifold for various reasons. The green part is non-manifold because we have points here in between the cubes on which we have various neighborhood connected components that touch into a single point. This would pose a lot of problems for various algorithms, so we would need to be able to detect such situation to take a decision to repair or remove the corresponding parts. Other non-manifold parts that we can see here on the red dataset are the edges here which are shared in between the cubes, because I will show you if I had a few transparency, then the neighborhood on this edge is not clearly defined, because I could go from this edge to the left, to the right, but also to the top or to the bottom. So we don't have a clear neighborhood here. So this would also pose troubles for a lot of algorithms. And of course, the last part also has troubles. There is an auto intersection of the mesh, and we also have 3 different neighborhood from the edges in the basics of the Y. So how could I detect such part into my meshes? Here it's obvious because it's a small one, but we could also try to detect this in a large mesh. We need our mesh to be triangulated surface. And here, if I go into information, I can see that this mesh is an unstructured grid in terms of VTK. In terms of VTK, unstructured grid means that it could contain 3 details, so it's not a surface. If we want to convert any dataset we have into a surface, we have a filter. So I will use the control space and ask ParaView to extract a surface. And this is easy. We have an extract.
So about control space, it's just a quick way to find filters, right?
Exactly.
Okay.
And it's a really powerful one, especially with the 5.13 release. So please, guys, use it. Extract surface is a simple filter that takes any dataset and extract the surface. I can see that because now if I come back into the information panel, I see that it's a polygonal mesh. In terms of VTK, it means that it's a surface mesh. And if I show the surface with edges, I see that I have quads here. In fact, I could inspect the kind of cells I have in my mesh using, for example, the spreadsheet view, where I select the cell data, and here I have all the cell types in my datasets, and I see that those are quads. I want triangles. So how could I have triangles? Let's try to ask ParaView for triangles into the same window than previously, and we have a triangulate filter. Okay, let's use the triangulate filter. Let's come back to the surface with edges, and here it looks better. How can I really double check that I only have triangles? I will try to extract cells by type. I have a filter for that too. And here I can select all the kind of the types of filters that VTK know, and I will try to extract everything but triangles.
So it should be empty.
And it should be empty.
Okay.
And indeed, in information, I see that the number of cells is 0. So every cell I have here are indeed triangles. Okay, so my check is done here. Now I will be able to use this dataset with Westphal and TTK to check the dataset. So I will first introduce you guys to the manifold check filters, which is provided by TTK. It's a filter that will describe the neighborhood around each point and each cells of your mesh. So once I have applied these filters, for now I don't see any difference. The main thing is I have new arrays which have been added to my dataset to describe the neighborhoods of each element. So for example, if I try to inspect the neighborhood of vertices, I will use the vertex links component number array. And as we can see, we have an indication here on the specific points that were problematic on the mesh. Here we can see that the number of connected components in the link of these points topologically are not 1, they are 2. It's invalid, so it's a non-manifold mesh in this regard. Yeah. If we want more information about the edges, we also have an array for that, the edge link component number. And this one, when we look at it into the dataset, we can see that it's correct. It's successfully extract the edges we talked about previously, where we had those invalid neighborhoods with 3 or 4 value depending on the part of the mesh we are. So what about a large data set that would correspond more to a real use case? I will come back into an empty pipeline with my ParaView and open a larger mesh. Okay, so here is a small data set. Visually it looks okay. Let's inspect this mesh to see if there are any troubles with it. I will use the manifold check plugins once again and inspect the results of my mesh. So if I look at the vertex links component number, I will need to rescale this, and we can see that it's 1 everywhere. So there is no problem with vertices here on this mesh.
So you're using the scalar range to check, right?
Yes, the scalar range.
It's automatically from the minimum to the maximum. If
exactly.
It's all ones, then it's fine. Okay.
Exactly. There is no value greater than 1 here. It's good. If I go into the edge link component number and I will rescale it again, we can already see in the mesh that there is here some parts that looks like problematic. Let's zoom on this part and try to understand what's the problem. I will highlight the triangles for you guys to see, and we can see here we have triangles which are obviously overlapping in a bad way. The edge here on the top of this triangle is not connected to anything, so the mesh is not even watertight. That's a problem that we will need to solve and that we can identify easily with the manifold check. Let's try to see if we have any other problems like this in the data sets. So I will go into View and Find Data, and I will try to find on the manifold check every cells on which the edge link component number is greater or equals to 3, which correspond to degenerate cases. And if I try to find this, I see the parts that we were talking about previously, but more of them are present in the dataset. I will do a more of less opacity here, and you can see that we have different parts in the dataset which are problematics. So how could I remove those parts? What I propose here is just to extend a bit our selection, so we are sure to take every edges which are problematic, and to remove those parts to remesh locally, so we will close all the little holes that we have created. So I have increased my selection with the plus here, and now I will just extract. I will need to invert first and extract the corresponding cells. So I will kind of rebuild my mesh with holes where we had troubles previously. I could identify these holes with a native ParaView filters, which is the feature edges. Just to show you, oh, I can apply these feature edges because I need to extract the surface. Once again, I have an unstructured grid now. So extract the surface, apply, and feature edges. And here I just want the boundary edges. And if I apply, oh, I will...
Sorry, Charles, you're outside of the camera.
Oh, sorry. I will highlight here in white, and we can see that we have extracted the opened boundaries of the dataset. So it's another way to see if the dataset is watertight or not with a native ParaView filter this time. So let's come back into the mesh which has holes in it. Before I show you how to close these holes, I want you to show how we have in Westphal a filters which is aimed to identify troubles that we can have with your mesh too. So in Westphal we have a mesh checker filter. It can check for different things. Here we will just want to check the water tightness of our mesh, and if we do apply, there is a warning here that shows us that the input is not closed. So this means that we have some troubles and we will need to close the mesh for Westphal algorithms, for most of the Westphal algorithms to work correctly. A good thing with this mesh checker is that we have an attempt remeshing, repairing mesh option, and if we use it, Westphal will directly try to solve the issue find into the mesh. And here, as we can see, if we apply it with this option enabled, the Westphal will tell you that the initial mesh is not closed, but then that it managed to successfully close the mesh. And if I come back here into my results, this time it has been closed. What happened under the hood? Under the hood, we simply used a hole filling algorithms, which is also available as a Westphal filter. So let's remove this mesh checker and close the mesh ourselves manually. We have the Westphal hole filling algorithm, and as you can see here, you can even drive the continuity of the fairing. It's just how we will interpolate around the wall to get something which is more flat or something which will be more curved to go around and have a smooth shape. And if I apply this,
see that you can give it a selection. What is it used for?
It's for performance reason. Here I don't give any selection, so it will try to close everything into the mesh. But you could select already the edges which correspond to your holes, and so Westphal will focus only on these and close only those. So it's a way to get more performance.
Okay.
On such a small hole, the fairing continuity is not so visible, so if I try to move it, you won't see any difference. But if you are working with CAD, for example, it will be very obvious if you try to go flat or curve around a larger hole. So you can move this parameter to see how it impacts the mesh in a more curved situation. here we are with the filling of the mesh. So it's a way to repair some simple problems that you may have into your mesh. Now, what if I want to remesh everything, to downsample or to source, to have a more finer resolution of my.
So we have a question
mesh.
from Tuan.
Yes.
Who asks, what does the fairing continuity do again? So he's asking again about the fairing continuity.
So let's imagine we have a curved shape, and in this curve we have missing triangles, which means that we have a hole into a curved shape. I may even try to create one. I will just try it just after I end my explanation. The fairing continuity will see how the newly added triangles will try to respect the global shape of your mesh. If you have a fairing continuity of 0, you will just create a flat surface that goes as quickly as possible from the boundaries to close the holes, but it may create kind of a bump into your smooth surface. On the other side, if you go into a fairing continuity of 2, Westphal will try to use second-degree polynomials to go around the curves and keep the smoothness of your mesh. So it's just a way to drive this. I will try to select some triangles and show you. It's freestyle. I'm not exactly sure of if everything will go as expected, but I think it should. Invert selection and extract, so I will be able to create.
So you're adding a hole, right?
Yes,
okay.
I'm adding a hole, and it's a hole in a curved part.
Okay.
So now I have an unstructured grid once again, so I need to extract the surface. This is something we often need to do dealing with the kind of meshes we have here. And I will go to the hole filling algorithms once again. If I have a fairing continuity of 0, as you can see, the mesh is closed in a brutal way. It's kind of really flat. And if I have a fairing continuity of 2, up, it's much better. I try to go around the shape of the smooth part. So that would be the goal of this parameter.
Okay. I think that's quite clear.
So let's come back into the remeshing part of this tutorial. We have different way that I would propose to update the resolution of your mesh. ParaView has some great decimation tools that would be able to reduce the resolution of the mesh. And in Westphal, we will propose 2 filters to also update the resolution. The first one will be the isotropic remesher, which will try to create a new mesh around the existing one and trying to keep the shape around the mesh. The main parameter that you would like to play with is the target length, which corresponds to the size of the edges of the triangles on the resulting mesh. You need to know your datasets to know which size you want. Here, 1 is much too large, we won't see anything. I will start with something which is much thinner, like 0.1, and apply. And here we can see that we have sub-sampled our mesh a bit. Let's try not to interpolate attributes so we are not bothered by the normals. And I could also play with this parameter to reduce it a bit more, to have something which comes closer to the initial shape of our hand. What is interesting here is that, I don't know if you have seen, guys, but there is a little part here that stayed from the original mesh, even if I have like a too large version.
Can you zoom on it, because it's not super clear?
I think with the edges it's clear.
Yeah.
Here we have seen that there are some initial edges which are kept from the original meshes. In the case of this dataset, it makes no real, there is no real interest to do so. But in CAD meshes, for example, that's often that you have sharp edges that you would like to get into your output, because those are important parts that you do not want to refine. And for this, we added a protection angle parameter into the isotropic remesher. And here, this is because in the initial mesh, we have some sharp edges into this part of the hands that those are kept. I can just choose to to protect angles which are larger, so we remove those parts too, and then I have a smoother hand.
So you remove the refined part, because
exactly.
In that case maybe you don't want it, but if you want to keep it, just keep the protection angle low.
On the other hand, if I go into a really small protection angles, most of the things will be protected, and so I have almost the initial mesh into the result. So you may want to play around with this parameter in a real world scenario. So here I have my hand. I have refined it more or less regarding the initial the initial mesh. Another way to get a manifold mesh from, I would say, from any kind of meshes, because this is really flexible algorithm that we have in Westphal. It's the alpha wrapping. It can take any polygon soups. It could even be a point cloud, and it will try to remesh regarding some parameters that I will show you. So the alpha wrapping algorithm is really powerful. So
just to make sure I understand, so, it's a bit similar to Delaunay, just another algorithm to do something similar to what Delaunay does.
The alpha wrapping, in some way, yes, but it works really differently, because the way Delaunay works, it's just connecting things which are close enough.
Yeah.
Here, the alpha wrapping will basically create a huge sphere, a huge convex hull around your dataset with a given resolution, and then it will try to push on every part of this convex hull to go into your datasets and make the new one as close as you indicated to imitate the shape of the datasets. So you have two main parameters. Alpha is the resolution, kind of the one we saw with the isotropic remeshing, and we have an offset that I will voluntarily here increase to show you that we don't get in the existing dataset, but we have an offset which is kind of a distance from the datasets that we would like to respect. And if I do so, here I have created a new one, a new dataset. We see here the resolution with the edges shown on the screen, but we see also how it's larger than the original hand. And if I reduce the offset, I will get closer and closer.
So here the original topology is not used at all, right? Only the points.
The points and the cells, because the cells are also constrained for the algorithm to respect, so it cannot push in between the points if there is a cell.
Okay.
So those are walls basically on which you can't go through. That's why it's different from Delaunay.
Okay, got it.
And here you can see with the current attributes that I have kind of large triangles and a large offset too. I cannot go in between the fingers, so I would need to reduce the size of the triangles by reducing the alpha, and maybe also reduce the offset to something really small to be able to remesh and go faster, to go deeper into the fingers in my mesh. And as you can see here, the finer the resolution you want, the longer these algorithms takes. But at the end, you can have really, really nice results.
We have a question. Maybe it's related to whole filling, I'm not sure. Is there from Nav, is there a way to detect sharp spikes and only locally smooth them and not other parts? Maybe you have already explained that and I missed that.
I haven't talked about the sharp and smooth things yet. We have indeed a smooth algorithms. So to detect the sharp parts, that's a good question. The feature edges would allows you to extract only the edges which are above a given threshold. Let's remove this. Here, for example, I know I have some here, so let's try to apply a feature edges here. And as you can see, there is a feature angle. So now I don't want boundary edges. I just want feature edges which are above a given angle. And if I apply this, you can see I have extracted different angles, different sharp angles into my data sets. But what you would need in your case would be to also be able to smooth only on those parts. This is something that TTK could do. I'm not sure how you would attach the information of the extracted edges on the data sets. I would need to think about it. But then, just to show you a bit, there is a TTK geometry smoother algorithms that can take a scalar mask. This scalar mask is an array attached to the points, and the points which are masked with this array, with a value of 1 or more, won't be displaced by the smooth algorithms. All the other one will be smooth. So for example, if I show you here into this data set, as you can see, the smooth is a simple convolution on which you just move a bit the points to get closer and closer to its neighborhood.
We need to move forward a little bit, I'm afraid. We have another question. Is there any way, from FV Ghoul, is there any way of getting Westphal under Windows?
you need to compile it yourself. So yes, but it's a bit complicated because you would need to compile Sigel, you would need to compile MPFR,
yeah,
things.
These things are hard to compile on Windows because it's GNU thing. So maybe the simplest way maybe to use WSL, but we did not check that. So you may have to, you're a bit on yourself on your own to do that.
Sorry.
Another question, is it possible to convert it back to a volume mesh? I assume Krupal means to actually have internal cells inside.
For now, no. Sigel has the kind of algorithms that would be useful to fill a surface mesh and come back into a 3D volume mesh, but these are not exposed into Westphal. At least it's not exposed yet. That would require some development. I hope it will come into the future, but for now the answer is no, not yet.
Okay, no more question. Maybe let's wrap it up.
Yeah. So I hope you guys.
Go back to the slide.
Yeah, you're right.
Sorry.
So yeah, we already had some questions, but if you guys have more questions, do not hesitate to add them into the chat. We will try to answer them just after. What we saw today are how to install different plugins to ParaView, TTK, and Westphal. We have here a reminder of the different parts which are needed to install them. And keep in mind that Westphal is based on Sigel, which provides a lot of geometric algorithms. And we saw together how we could use these two tools to check for the mesh in terms of water tightness, in terms of manifoldness, and then to repair locally the mesh when we could, or to eventually remesh everything when there was no other solutions. And there is also in Westphal different algorithms that are provided that could allow you to smooth the mesh. We saw that, but we didn't have had the time. We could also, I could have shown you how we could have boolean operation between meshes to compute the difference or the union of different surfaces. There is a deformation mesh and deformation algorithms on which you can displace some part of your meshes into a given position. There are a lot of algorithms. So guys, just please have a look at the Westphal documentation. It's really powerful.
So something else, if you have any questions, anything that you want to do with Westphal, please reach out to us. We'll definitely be able to help and maybe try to do something together. Another question from Nav. Will this webinar and presentation be available so we can rewatch? Absolutely, they will be not right now, but they will be available in a few days on the same link. It should work correctly. Another question from Nura. Is Westphal the first plugin which integrates Sigel into ParaView? I think so, yes.
Made by Kitware, at least, for sure.
And in any official way, I would say.
Yeah. Maybe there was some other project that I was not aware of that did that.
But nothing that we know of.
Yeah.
Okay, no other questions. Maybe let's talk about the next webinar.
Yeah, there will be on the 8th of October a webinar about dynamic simulation with open radios. So you have here a small highlight where we show how you can break your phone with ParaView.
Well, with open radios, but you can show it in ParaView.
Exactly. And so yeah, guys, please feel free to join. It will be really interesting too. So.
Yeah, this webinar is done by Open Radios and Kitware together, so make sure to tune in and have a look. You need to register to the webinar. It's a little bit different organization, but you can take a look. All right.
Thank you, everyone, and I hope you learn useful things for today. And yeah, please do not hesitate to reach us even on Discourse for Westphal questions. So the ParaView Discourse is a great place to be.
Last question, Westphal coming to Windows. We already answered that. Sadly, you have to compile by yourself. It's not that easy. All right. Thanks, everyone. Bye-bye.
Bye-bye.